Alright, so today we're going to be talking about basics of the refrigerant circuit, charging, checking charges, setting charges. It's like most classes that I give, what you want me to tell you is not going to be probably what I tell you. Because what I most often get questions about are things like, what should my superheat be? Or what should my suction pressure be? And I'm not going to answer that question. I'm going to answer the bigger question, which is how can you know what it should be? How can you put together a lot of different information and actually come up with a conclusion about what is correct given the conditions that you're experiencing? And there is no one simple answer to this, to that question, because very rarely are we actually working on brand new systems unless you're doing installation. In most cases, we're working on systems that are not brand new. Therefore, the way they're going to run is not going to be exactly the same as they did when they came out of the box. So we're going to be kind of talking about how to understand the different things that are going on in a system that dictate how a charge is set and how a charge is checked. Okay? So to start with, I'm going to do a quick review of the concept of pressure-temperature relationships. I talked about how temperature is average molecular velocity within matter. So the higher the molecular velocity, the faster the molecules are moving, the more pressure they exert on the outside of whatever space they're contained by. So when we're talking about a refrigeration circuit, we're talking about a closed system, meaning that the refrigerant is completely encapsulated inside this system. So depending on the type of refrigerant that you have, depending on the temperature conditions, depending on the pressure, all those things affect the ways one affects the other. So whenever you have an increase of temperature in a closed vessel, you also have an increase of pressure in that vessel. If we were to take this room and we were to seal it off completely tight, and we were to start to heat this room, that you would actually increase the pressure inside this room because the molecules are moving faster, therefore they're exerting more force on the outside walls. You with me? So the temperature surrounding this room and the temperature in the room affect the pressure that would be in a sealed room. We're not used to dealing with sealed containers when we're typically working with things. We think about, in regular life, we think about boiling water, boiling at 212. Well, like we talked about, boils at 212 because it's an atmospheric pressure. But if we were able to affect the pressure that surrounded that vessel of water, we could also affect the temperature at which it boiled. Okay? So when we're looking at a set of refrigerants, so I'm going to jump, that's a basic, I'm not going to connect all the dots here. I'm just kind of jumping from one to the next just so we can make sure we're on the same page. So when we're talking about a refrigerant gauges, what we're looking at is we're looking at the pressure that exists inside the sealed container. And we have essentially two constants. The constant one is we know what refrigerant it is, right? We're making that assumption. Now, could you figure out what refrigerant you had based on the pressure that you saw inside the system?
Yeah. You would be a few other things.
You could have a pretty good guess. And how do you come up with that pretty good guess?
Well, if you go to a unit and your pressures are your 75 psi and your unit's frozen, there's a very good chance it should be 410.
That's a very practical example.
So the larger principle would be comparing the pressure to the temperature of the lines.
Well, what we tend to do is
looking at data, please.
looking at data. Well, we had a case the other day. I don't remember who it was. It might have been you, Leslie. We went to a system that had someone had put in like R422D or something. Yeah, some other type of alternate refrigerant. Well, then at that point, it may have very similar pressure temperature characteristics to R22, say. But how can you know whether or not it's R22 unless someone tells you? Well, you can't know exactly, but you can get a pretty good idea, and here's how we do it. As long as that refrigerant is a mixture of liquid and vapor, that's what we call at saturation. It's a mixture of the two. It will have certain pressure characteristics at certain temperatures. So what you do is when you walk up to a system and it's off, that's what we call static pressure, meaning that you don't have anything affecting motion of the refrigerant within the system. So you hook up to a system that's off, you call that static pressure. When you take that static pressure, assuming that there is a mixture of liquid and vapor in that system, which there should be unless it's almost completely flat, you can then take a temperature around that system. So take it, in the condenser, generally speaking, that's where most of the refrigerant is held. Take a temperature around there, and then You can look on your saturation scale in here. In this case, R22 is our green scale here. And you can go up to, say it's 75 degrees outside. You can go up to 75 degrees, and you can see that that's going to be right about 135 psi. So if you hook up to a system, and it says 135 psi static pressure, then you have a pretty good indication that it's R22, because it's in that saturation phase. Now, that's another assumption that we're making. How could you know that? Well, there's a couple different ways. We won't go into that. But generally speaking, when you walk up to a system, you would assume that it would have liquid and vapor in it. Now, why can we make now why can we make that sort of leap of faith? Why can we say, that it is R22? Well, it's experience. You walk up to a system, you read the data plate, those types of things. We really only have two different types of refrigerants that are generally used in residential HVAC systems. So we're really just kind of comparing the two. R410A runs much higher pressures even in static. If it were an R410A system and it was 75 degrees, then we would be running closer to about 225 psi with 75 degrees temperature around it. So what we're essentially doing in this whole exercise here is not establishing how to figure out what refrigerants are, but establishing the idea that there are these constants that exist, that temperature does affect in a constant way the pressures that are exerted by the molecules inside of a system, as long as we know what the molecules are. Okay, so if we have that constant, knowing what the molecules are, then by knowing either the pressure or the temperature, we can then get an idea of what's going on in the system, whether or not we're in the saturated state, whether we're in the vapor state, or whether we're in the liquid state. And that's what we're trying to establish, because when we talk about refrigerant being in a mixed state, we're saying that both vapor and liquid are existing here. Well, if it were to be colder than that temperature that was indicated, if the temperature of the line, say, the refrigerant line or the refrigerant in that system, was colder than the pressure-temperature relationship at saturation, then we could say confirmably it's a liquid. Because in order for it to cool, in order for it to get colder than the temperature of saturation, meaning a mixed state, think of it like boiling water. Boiling water is 212 at atmospheric pressure. That's what we call saturation. It's at that point where it's completely saturated with heat at this given atmospheric pressure, and now it's having to change state because it's completely saturated. So if water is colder than 212, we can say at atmospheric pressure it is liquid. If water is hotter at atmospheric pressure than 212, we can say unequivocally it is vapor. If we say that it is 212 at atmospheric pressure, we can say that it is
At saturation.
It's at saturation. It's boiling, because we know what substance it is and we know the pressure. That's all what I'm saying. So by knowing those pieces of information, we can know something about the system. Now, if we could say, for example, let's say we can observe the boiling. That's what we're talking about in terms of a vessel of water. We're just essentially using logic here. You look at a vessel of water sitting at sea level and you see it's boiling. You can say that water is 212 degrees, right? Okay. Now, what if I were to see a vessel that had glass over it, and I could see a thermometer in that, okay, and I could see that thermometer, that water was boiling, and that thermometer read 300 degrees. What then could I assume?
That there is a higher pressure inside of that sealed.
Inside that sealed vessel, correct. And so what we're doing is, here's what I'm establishing. We're using logic based on what we know in order to surmise. We can know what's going on with what we don't know, okay? Now, inside of a sealed vessel, we don't see what's going on. So we don't know for a fact, for example, I can walk up to an air conditioner, I can't say, without some data, I can't say it's boiling there, it's liquid there, it's vapor there. I can't do that unless I've taken the pressure and temperature readings, and then I can tell that, right? So, let's jump right into what's supposed to happen inside of an air conditioner. For those of you who may not know, what do these two knobs here do? What's the purpose of them? What's actually happening inside here when I open and close these valves?
One way or the other.
Into the manifold.
You're allowing it to flow inside the manifold body. A lot of people who look at a gauge like this will think that what you're doing here is somehow affecting what you read on the gauge, but it's not at all. These hoses still travel through the gauge regardless of whether or not these handles are open. All these handles are doing is allowing you to mix in between these. So if I were to open this knob here, what two lines am I mixing together?
Center
and blue.
Yellow and blue. If I shut this one off, and I open up this one, which two lines am I mixing together?
Yellow, red.
Now I'm opening up here. If I open up both, now what am I
Yellow,
doing?
red, and blue.
Now I'm mixing all of them together. Does that make sense? I'm making a connection between all of them when both of these are open. Does that make sense?
Yep.
You with me here? Okay. So it's got nothing to do with what reads on the gauge. So if I take this, if I take my suction gauge off here, let me first tell you that this is the compressor, condenser, metering device, evaporator. Where am I hooking this gauge to? Someone describe to me. Where is this gauge hooking to?
Right before it goes in the compressor.
Right before it goes in the compressor. So I'm hooking here, okay? On a typical residential system. And with this one here, where am I hooking to?
As it comes out.
As it comes out of the condenser.
As it comes out of the condenser. So right here, okay? So am I hooking up right before it goes in and out of the compressor? No, I'm not. I'm hooking up before it goes into the compressor, and I'm hooking up after it comes out of the condenser, okay? So let's go, for those of you who don't know, which most of you probably do, but let's go through the different states of what occurs inside the system. So we've got our compressor, which is a giant pump. It actually compresses the refrigerant, okay? So what state is the refrigerant in right here?
High temperature vapor.
High temperature vapor. High pressure, high temperature vapor. What state is the refrigerant in here? This is evaporator coming back.
It goes in liquid.
We got our direction here. We know this is our compressor. So you can figure
Low
it out.
pressure vapor.
Low temperature, low pressure vapor. Okay, so it goes into the compressor, low temperature, low pressure vapor, comes out of the compressor, high temperature, high pressure vapor. Right? Okay? Why doesn't it just become liquid as soon as it's compressed?
As you increase pressure, you're also increasing the energy per volume.
Correct.
So you're making it hotter as you compress it.
Correct. It has the same amount of heat it had before. You're not actually increasing the amount of heat, but you're increasing the temperature. Do you remember how we talked about that? Because by reducing the amount of volume that it has to operate in, you're exciting the molecules, so the molecules are moving faster. So it's directly proportional, meaning that the more you compress it, the hotter it gets. So you can never turn something into a liquid, because as you compress it, it just gets hotter and hotter and hotter. So you've got to dissipate that heat in order to condense it. In order to turn it into a liquid, you've got to allow that heat to dissipate. Okay? So we reveal heat, we expose it by compressing it and driving the temperature up. And now by compressing it and driving the temperature up, now it flows through the condenser coil. Okay? So now what is the state of the refrigerant right here?
Liquid.
Yeah.
The state of it is here. Now it's a liquid. Because in the condenser condenses, you have high temperature, high pressure vapor going into it, it condenses, and then it comes out as a liquid. Okay? Now, what is the name of this line? The liquid line. That's a tricky one, right? Okay. Liquid line because it's liquid. What's the name of this line?
Discharge.
Okay, how are they different?
Well, your discharge
Different
line,
states.
the pressures are a lot higher.
Different
because they're high
pressures.
pressure vapor.
They're actually not that much higher. The only difference
It's
in
definitely higher though.
it is higher. The only difference in pressure though is actually the pressure drop through the condenser. It's actually just pressure drop.
So
It's
just
the same
the
pressure
state.
because you're forcing it together. It's that it's changed state because now you're dissipating heat off of it and allowing it to condense down, settle down into a liquid state fully. Does that make sense? Okay. So high pressure, high temperature vapor here goes through the condenser, condenses, comes out liquid, hits this. What is this? What are some common metering devices?
TXV.
Piston is a term that's used, actuator, orifice. Back in the day, capillary tubes are still commonly used in refrigerators and ice machines, which is just a little tiny tube of copper. So what's the purpose of this?
To back up the
Liquid refrigerant and allow
Allow
expansion,
just enough.
rapid expansion.
It acts as a center point between the two halves of the system. And so not only does it, so really you can think of it in two different ways. You could describe it two ways and then both would be correct. You could describe it the way that Nathan Bishop just did, which it backs up the liquid, which is true. Because without your metering device, you don't have adequate pressure over here. In order to have pressure, you have to be building pressure up against something.
And that's what's causing the pressure difference though.
Correct. It's so over here we have the high side of our system, and over here we have the low side of our system. So your compressor and your metering device split those two halves of the
That's where your
system.
difference takes place.
And so where, if you guys have ever seen a system, where is the point in which you start to see temperature change from warm to cold?
After the
Right after the
metering
After
device.
the metering.
Directly after the metering device, but even more so than that, because we tend to think of an expansion valve as a whole part. We always like to think of things as entire parts. but it's the exact point at which the pressure drop occurs is where you see the
So
difference.
right
So it'd be an
orifice.
evaporator.
Right where that orifice is, right where it goes from big to small, right where it restricts, that's where the pressure drop occurs, and that's where you see the difference in pressure. Okay. So what starts to happen now as the pressure is reduced?
Starts to boil.
Starts to boil because now you've reduced the bounds on those molecules, and they start to rapidly expand. Okay. Now we're once again.
So it's boiling, even though there's at this point no energy difference. There's no increase in temperature.
Well, but there is. Well, it's
Well,
no, because you're still absorbing heat from the space around. You can't have boiling without heat being absorbed. But heat is being absorbed because at that instantaneous moment, because the pressure is dropped so quickly, what you're essentially doing, if you think of it in terms of water, is you've taken this water and you've decreased the atmospheric pressure on it until it's boiling at like 40 degrees Fahrenheit. Well, the space around is warmer than 40 degrees Fahrenheit, so now the space around starts to give its heat up to that refrigerant that's in the evaporator as it's boiling and changing state. Okay, so this is the point where it transfers from high side to low side. What is this line called? Between the metering device and the evaporator coil. This is called the expansion line. Okay, now, where do you see an expansion line? There is a place that you see an expansion line, but you just don't think of it very often as an expansion line, because in a regular home air conditioner, you don't have an expansion line. You have your expansion valve that's mounted pretty much right on that evaporator coil, and it just goes. Really, these two are kind of married into one almost.
Well, isn't the evap coil your expansion line because you're expanding through the evaporator coil?
It is. I mean, this is really just becomes an extension of the evaporator coil, really, because you have what the state of refrigerant in this is what we call as flash gas, meaning it's in the process
And
of
it should
boiling
be that
off.
way pretty much from there straight throughout the evap.
Correct, pretty much, yeah. Why do we insulate the liquid line on a ductless system? Because it's not a liquid line. Because it's actually an expansion line. Because the metering device is in a condenser and a ductless system, all these are in one place, and now you have a line that travels through there. So this is a cold line. So your small line is a cold line. I mean, it's because it's actually not a liquid line at all. It's actually an expansion line. It's a low pressure flash gas line, which is why it'll sweat. Now, they're not necessarily all that way, but that's how a lot of them are. So anyway, it is a real thing. I'm just using that to demonstrate expansion line is actually a real thing. It all just depends on how these are positioned. What I used to always say in class is I could build an air conditioner, I could take a condenser, put it over there, I could take a compressor, put it on the other side of the building, an evaporator over here, expansion line, and a metering device over there, and just hook them all together and it would still work. We tend to think of air conditioning systems in terms of an air handler and a condenser, which are a standardized grouping that we use in a split system in residential applications. But that isn't how it has to be. That's just how they do it, in production air conditioning. But thinking of an air conditioner like this, in terms of its four components and its four lines and the different states of the refrigerant in the lines, is much more accurate, and it will help you think much more clearly about what it is that you're accomplishing. Okay? Because let's give an example. Let's say you're on a commercial rooftop package unit, and a lot of times, where will the ports be on a commercial rooftop package unit? Which two lines?
Discharge.
You'll have a port here, and you'll have a port here. Okay? What happens if you're trying to take your soup up cool here?
You're not going to get a true reading.
You're not going to get a rating hardly at all.
You don't get any.
Because you're not going to get a subcool because it's going to be the same temperature, or actually higher, a lot higher temperature, because it's actually still in the vapor state, which means that it's going to be, the temperature of that line is going to be much higher than saturation. When any matter's in the vapor state, it's going to be higher than saturation. And there's no real way of knowing how much higher it's going to be. That's like saying, well, how can I tell how hot this air is going to be based on the temperature around it or based on the pressure? Well, you can't know because it's not in saturation. This air isn't in the process of boiling. So I can't really tell you anything about what temperature it's going to be.
There is no reference point. If it's in the
Correct.
process of boiling, it can't be much higher than saturation. So you have a window of reference.
It can't be higher than saturation at all as long as you know what the pressure is and you know exactly what the matter is that you're dealing with. If you know what the pressure is and you know what the matter is and it's in the process of boiling, it will be this temperature. In the same way, saying water will be 212 at atmospheric pressure at sea level. Okay? So anyway. So when we're starting to talk specifically about how we test an air conditioning system with gauges and what we're hooking up to and what we're reading, you have to understand this. You have to be very clear on what everything's supposed to be in each sector and what's actually going on throughout this system.
Could I just add real quick? Now, if you just get out of this room and go to a pool, to a heat pump,
Mhm.
and you're looking, it's the same way though, right? Because a lot of times your discharge line, your high side is actually your discharge line on the pool pump, depending upon whether it's before or after.
Correct.
the-
So practically speaking, here's what happens. You're going to be taking your pressure here and your temperature here. Okay, so that will affect it because you are going to have pressure drop. So your pressure here, maybe say it's 250 psi. Well, you can't use 250 psi as your number in order to factor in your subcool at this point. All right, because it's going to have dropped. Now, how much will it have dropped? You're going to have to kind of guess. At that point, it's not a perfect science, but you can get a good indication. You know, generally speaking, I'll say, all right, on a pool heater, I'll figure it probably drop 10 psi or 20 psi. You know, and that'll give you a general idea. But yeah, it's not exact at that point. It can't be. In order to take a reading, in order to figure out the state of the refrigerant, you have to be taking your temperature and pressure readings at the exact same point in order to be
Which
scientific.
you can't do.
Which you can't always do. Okay, let's give another example. People will say something like, and I'm jumping ahead of myself, but for the technicians here, someone will say, "Hey, your superheat, this TXV is supposed to maintain a 6-degree superheat." Well, where's that TXV maintaining the superheat at? At the evaporator, because where's the bulb mounted?
Evaporate.
On the evaporator, on the suction line. So it's measuring it here, and so we're taking a superheat where?
Outside.
Out here. Well, does that TXV have any idea whether or not that suction line's insulated, how long the line set is, any of that stuff? Whether it's got a 40-foot rise in a condo? No, it's got no clue. It's trying to do its job at the outlet of the evaporator. It doesn't know what's going on here. A lot of guys will say, "Oh, well, that's why you need to raise a port here, and you always need to take your hogwash." That's not. It's not how it works. It's not real life. Real life is you measure it here, and you have to, by taking some more readings, you know, you can go inside and take a temperature reading there, and you can get a good indication based on how long the line set is and everything else. You just have to use common sense, which is kind of what I'm saying. So anyway, so that's it. That's all I'm really going to say about this. If there's anything that you can memorize in the industry that will help you, as far as it pertains to what I'm going to talk about next, it's to stand there and write over and over again and say over and over again: compressor, condenser, metering device, evaporator. Compressor, condenser, metering device. I'm not kidding. Discharge line, liquid line, expansion line, suction line. Discharge line, liquid line, expansion line, suction line. When I went into AC school the first day, my instructor introduced me to everyone. Hey, yeah, this is the room. Here's the tool room. Da, 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 da. Okay, here's the board. All right, I'm going to write these 4. All right, here's what it is. Compressor, condenser, metering device, evaporator. Okay, I'm going to erase it. Do that for the next 2 hours. Come back to me when you're done. So you have it memorized. And then, okay, I'm done. All right, now here's the next thing. Discharge line, liquid line, expansion line, suction line. All right, now write in the states. Now split it in half based on the state of the refrigerant. Now split it in half based on high side and low side, because you do it the other way here too. So this is low side, this is high side, and then this is the vapor side. This is the liquid side. It's actually saturated liquid as it comes out the other side here, but you know, and so you just start to kind of build on that, and then he taught us, you know, to feel through the system with our hands. You know, all right, this is what a suction line should feel like. This is what a liquid line should feel like. Ouch, that's what a discharge line should feel like. No, seriously, because then it gives you an indication, especially when you're newer to the trade, to start to be able to tell. Ouch, that's not the liquid line. You know, that's the discharge line. I mean, that is what you end up doing. Not that I'm necessarily telling you to grab a discharge line here, but this is key to this, because if you don't ever get this, then you won't ever get what I'm about to talk about next. Okay, so now we're going to talk about checking and setting refrigerant charges. Okay, so I talk about the 5 pillars. I came up with that before I knew anything about the real 5 pillars. But so you have suction pressure, you have head pressure, you have subcool, you have superheat, you have air temperature split. Okay, we're talking, you know, generally about our regular day in and day out residential systems. This is nothing complex. We're not talking about chillers here and water splits and stuff like that. It's standard basic stuff. Okay. So, what is the most common thing in the industry when your average AC technician says, "Hey, that system's low"? What is he usually saying when he says that?
Saturation.
He's saying the suction pressure's low. Yeah, that's generally what he's saying. It means he's hooked his suction gauge up on an R22 system and he saw that it read 40 psi. Okay, or whatever. Now, if you did go up to a system and you hooked up your suction gauge and it read 40 psi, what does that actually tell you?
Nothing.
It doesn't tell you nothing. It doesn't tell you nothing. But what you could actually say is, okay, is it tells me the saturation temperature that exists within that evaporator, or
isn't it
generally within the
not
evaporator, but within the
completely-
suction line.
You're not completely, from the start of the coil to the end of the coil, boiling off.
Well, you don't know that because what I didn't tell you is it was reading 40 psi, but it's frozen to a solid block of ice. You know, so it doesn't tell you that. You have to have the temperature-pressure relationship in order to know whether or not that's the case. Because what's the other common cause of a unit running 40 psi suction?
Low air restriction.
Could be really low airflow. Right, the other thing could be frozen solid. And trust me, I've seen a lot of guys who will walk up to a system that's literally frozen, actually still has ice on it, starting to put refrigerant in it. I know this guy I rode with at one point in time, back when I worked at the old country. And he did that. He went to a system that was totally iced up late in the evening and just said, oh, I'm sure it's just low, I'll just gas it up. And so he added, 4 or 5 pounds to it and said, yeah, we'll come back tomorrow and check it again. And it wasn't. It was airflow totally, So I think I just had a cruddy filter in it or something. You didn't even check anything. So really, by itself, it tells you very little. Okay, what does an air temperature split tell you? Let's say you take a 20-degree split. You got it's 85 degrees inside, and I got 65 degrees coming out top of that unit. What does that tell you?
Again, it doesn't tell you.
Doesn't tell you.
Depends if your coil's dirty or.
Doesn't tell you much of anything.
Doesn't tell you if you're low on charge and you have a dirty filter in it as well.
Sure, you could be low on charge and have a dirty filter. Could be running 350 psi head, and the compressor's about to blow sky high. You got no idea.
Wheels completely filthy.
Could be any of those things. Okay, so by themselves, it doesn't tell you much. Now, when you start to get into actually checking the charge accurately, you have to get a little bit more detailed about what you're supposed to be accomplishing. So, let's say I'm supposed to have liquid here, but I don't have liquid. I have a mixture of liquid and vapor. How am I going to know that? Practically speaking, knowing what we know now, you don't have to give me any specific numbers, but I'm supposed to have liquid here because this is the liquid line, but I don't have liquid in that liquid line. How am I going to know?
That's what would make this noise.
Yep. Well, that's an experienced way of knowing.
I'm trying.
Saturation temperature?
Because
Pressure's low.
if I read the pressure here, and I read the temperature here,
Right, difference.
and they match at saturation. So if the saturation temperature is 98 degrees at that pressure, and the temperature is 98 degrees, then that tells me, just in the same way that if you measure 212 degree boiling water at atmospheric pressure, it's telling me that it's still a mixture of liquid and vapor, right?
Suction line's flying that cold.
Maybe not. But I'm just saying, specifically saying, do I have a solid line of liquid here or not? If you had a sight glass, you could tell, right? But we don't. So we gotta use our temperatures and our pressures in order to tell us whether or not we have full liquid here.
Why
Let's
isn't it
say-
industry standard to put on sight glasses on everything?
Because they really don't have any point, honestly. Sight glasses, the only point of a sight glass is for people who don't know how to read subcool. Because if you're reading subcool, if you have 1 degree of subcool, meaning that the saturation temperature is reading 98 and it's 97, what does that tell you? You have 1 degree of subcool and the state of the refrigerant here is liquid.
It's all liquid. Right?
Here's the problem: your gauges aren't that good. Because you could be reading 97 and now, oh yeah, I've got 1 degree of subcool. You may actually have 0 subcool. You may be reading 5 degrees of subcool and have 0 subcool. A lot of times.
So is that why as a tech, you'll say you want to make sure you have at least a couple degrees of subcool?
It's more than that. It's
Basically to
because
bank on
At least a
or-
couple gauges to cross.
it's more than that because there's more things at play here than just subcool. A lot of people, I used to even teach this back when I was stupid. I used to say 1 degree of subcool is actually the ideal subcool to have because that way you're running your lowest potential head pressure, and lower head pressure is good because that means less amperage. Wrong, because we're dealing with matter here, and the matter that we've got is a refrigerant, and the higher the subcool, the more density we have overall, meaning we're actually moving more refrigerant overall. The more refrigerant you can pack into a system, the more cooling capacity you're going to have, because we're talking about cooling capacity per pound or ounce or whatever, per weight of refrigerant. And so the more refrigerant you get into a system, the more cooling capacity you're actually going to have. Meaning that, I'm sorry?
Then you're gonna saturate the condenser.
Well, it's its own saturate the condenser. What do you mean?
Look, I'm trying to do vapor, and you're gonna saturate the evap plus
what you're saying is you're going to overfeed the evaporator coil as well. Yeah, right. There's other things that factor in there. What I'm saying is, though, I used to dumbly say, oh well, yeah, 1 degree of liquid is actually ideal, but you have to add more because you don't know how accurate your equipment is. Actually, that's not true. You know what the perfect amount of refrigerant to have in a system is?
What the data
Some
point
bad
says.
Yeah.
The exact amount that it's supposed to have in it. Meaning the exact amount it was designed for. Because if you add more than what it was designed for, then you're going to cause other problems. Meaning, like what Leslie said, you're going to overfeed the evaporator coil potentially. You're going to run higher head pressure, which is going to cause your compressor to run higher amperage. If you undercharge the system, then you're going to have less refrigerant density. You run the risk of it freezing up. It has to have the amount of refrigerant that it's designed to have, and then it will be running ideally. But the problem is that we're dealing with systems that aren't brand new, and aren't perfect. So we're having to try to figure out that kind of happy medium. So what we want to know here, as it pertains to the liquid line, is what we want to know when we're taking readings on the liquid line is we want to make sure that we've got liquid in our liquid line. That's step one. Second step is to try to take the readings based on what the manufacturers suggest in order to tell us, do we have a correct subgroup? Okay? And this is like what I was saying, it's super important that you make sure that your equipment is as well calibrated as it possibly can be. Recognizing that realistically, a 2-3 psi variance here, a 1-2 degree temperature variance there is not unrealistic. You're probably not going to do much better than that. Not only is our equipment not perfect, but we're also not actually reading the temperature of the liquid in the line. We're reading the temperature of the copper around the liquid in the line. So that also makes it a little bit of a difference. So once again, we're not functioning in a perfect world. Okay? All right, so let's say that we are working on a ductless system and we can actually read the pressure and temperature on the expansion line. Okay? What do we want to actually see is going on in this expansion line?
We want to see a mix of liquid.
Exactly.
Yeah.
Because you want to see that flash gas. It's in the process of changing. We call that boiling practically. In our world, we see boiling. You can call it flash gas, you can call it mixed vapor and liquid, whatever you want to call it. But that means that if we can measure a temperature here, we want that to be matching what's on our PT, our pressure temperature correlation scale on our gauges. We want that to be matching saturation because we want to be able to prove that the refrigerant here is in that change of state. Okay? Now, we know that it's flash gas here, meaning it's in the process of changing. Now let's say we got, this is our evaporator coil here. And it's here and here and here and here. It's got all these tubes feeding in, and then it hits the suction line. How far through this evaporator coil do we want to see it changing state from liquid to vapor?
You want to use the whole coil.
Yeah. Throughout the whole coil.
Well, if your whole coil was change of state, then what would your superheat be right here?
Yeah, I mean, you don't want it to come out the other side, but you want it to fully change state probably 3/4 of the way through the coil. Maybe.
Right. That's the balance that you're making there, because you do want to use up as much of the coil as you can, as is reasonable to use up. But you don't want boiling liquid, change of state, refrigerant traveling down the suction line towards the compressor. Why?
You sludge your compressor.
You slug the compressor, which means what? Yeah, you'll get liquid back in the compressor, which dilutes the oil and causes oil migration and all kinds of different
Okay,
nasty
so then
stuff.
on that evap coil, is it the amount of refrigerant that's telling you at what point it changes state right there? Because it's not in the coil, right?
It isn't just that. You've got two different factors here. You've got the volume of mixed refrigerant that's traveling through it, and you have the amount of heat absorption going on around it, which is the reason why if you take an evaporator coil and you throw a bunch of cat hair on it, what does it do? What does it do to the pressures? You guys know because you work on it every day. You throw a bunch of cat hair on a coil, what does it do? Evaporator coil.
Drops
the pressure.
Why is that?
Because it's
Right.
slowing the absorption, or slowing the airflow across it and is absorbing more heat.
It's absorbing less heat.
Or, yes.
You're exposing this coil to less heat than you would normally have. Okay. Now, why does that affect anything? Well, because now you've got this liquid. It's got to be boiled somehow, right? What you've just done is you've turned down the heat on the stove. So think of it like a stove. Think of this evaporator coil. I know it's counterintuitive because the stove's hot and it's boiling, but it is. This is a big boiling pot of water. Okay, and we want to boil off this water. If you throw cat hair on it, you've turned down the stove because you're now exposing that to less heat than you would have in the first place. Because remember, all that air that's going across that coil, that's giving it heat. That's the flame underneath the boiling pot of water. Okay, you reduce that, now you're not exposing it to as much. Because remember the pressure temperature relationship once again. If you don't expose it to the heat that you normally
that's
would
how
have,
it
now it's not
freezes.
expanding as much.
That's how it freezes. Because
Correct.
it just sits there and it's not being boiled off.
Because
It
that's
just gets
still-
colder,
Because the
colder,
rate,
colder.
the amount of refrigerant remains constant. You're
Oh,
still
okay.
flowing that same amount of refrigerant through there, and that coil just gets colder and colder and colder because it's not exposing to the heat. The pressure keeps dropping lower and lower and lower. Hits 32 degrees saturation, ice, and you're done. If it wasn't for the fact that coils formed ice, we would run them as cold as we could. Ice is really the only thing that keeps us in direct expansion air conditioning, which is what we work on. That's the only thing that causes us trouble. If it wasn't for ice, we would run coils at minus 10 degrees. But the problem is we build ice, it blocks the coil, and now you're done. Not getting any air through it anymore. So, next line. We've got our suction line here. What's the state supposed to be in the suction line? Fully vapor. The compressor only pumps vapor. Okay? How can we prove that it's vapor in the suction line? We prove it by superheat, which is what? What does superheat mean?
Difference in temperature between the center and the coil and
What's the difference in temperature between what it actually is running, what the line is, and what the saturation temperature would be for that refrigerant?
Correct. Jeff described it in an interesting way. What Jeff said is that it's the increase in temperature from the middle of the coil to here. That's a way of saying it, which is really saying a difference in temperature, an increase of temperature from saturation, meaning from the temperature that it was in which it was boiling, to the temperature that it now is, that it's fully vapor. Because just like that 212 degree pot of water, you can only heat it more until once it's fully vapor, and then you can continue to heat it and it will get hotter. In the same way, until this boiling pot of water completely boils and completely becomes vapor, it cannot get warmer than the saturation temperature. And for us, saturation temperature we find on the gauge because the pressure fluctuates, therefore the saturation pressure fluctuates. But you look at that gauge and it tells you that refrigerant, we know what the refrigerant is, so we can see that, okay, that's our saturation temperature. If it's higher, if the actual physical temperature of that line is higher, then we know that it's fully vapor. If the physical temperature of the line is colder than saturation, then we know it's
Liquid.
fully liquid. If it's the same as saturation, then we know it's mixed state. It's not necessarily flash gas. It's flash gas when we're talking on this side of the system, but in the condenser coil, it's also saturation. If you were to take your thermometer and stick it, get a good reading right in the middle of your condenser coil, you would be reading the same saturation as you can read on your gauge, as long as you can get them close to each other. Because at that point, you're reading it changing state, but it's the other direction. It's changing state from a vapor to a liquid.
So if it's,
Okay? So it's actually, at that point, it is condensing. Here's the important thing. I had a guy who I worked with, a good technician, who would write up on his invoices negative superheat. He would write down, superheat, -2. Does anyone see a problem with that? Because negative superheat is what?
Subcool.
Is subcool. And so what he's saying is, because what does subcool tell you?
That it's liquid.
It's fully liquid. So what he's saying is this suction line is 100% liquid. Is that possible?
Yes, but not if it's working.
It's theoretically possible, but there's no running air conditioner that exists in that state. So what does that tell you?
That his tools are miscalibrated.
Correct. It tells you that his tools aren't working properly. So probably what he had was 0 superheat, but he wrote -2. So if you ever have a -2 superheat or a -2 liquid subcool, that's not telling you that you actually have negative superheat or subcool, because that can't happen with a running system. But what it is telling you that, oh shoot, I probably have a 0 subcool and my gauges just aren't right, or my thermometer's not right. Because again, you're talking about two different devices, unless you're using an S-Man 3, which are trying to tell you, trying to give you comparisons, so that way you can decipher whether or not it's liquid or vapor, right at that point, or changing state. Okay? So let's get down to the nitty-gritty now. The 5 pillars. We're measuring air temperature split. We're measuring superheat. We're measuring subcool. We're measuring suction pressure. We're measuring head pressure. Okay? The only way you can get any really good information is to have at least 4 out of 5 of those. Okay? at least 4 out of 5. Now, if you've got a, let's say you've got a TXV system, you walk up to it and you're running 40 suction on the system, and you hook up your high side and you're reading 150, and the suction line, and the suction line when you come out is warm. What is that going to tell you? Experienced guys here, fill this out.
Low on charge.
Because I didn't even have to really check the actual superheat on the suction line. I'm reading 45 psi on an R22 system, which on this is going to be about 20 degrees. Okay, and if I grab that line and it feels just barely cool, well, that right there is telling me about a 40-degree superheat. I don't have to
You feel
use
the air
a thermometer to tell me that.
You know, also use your hand over the condenser fan motor.
It can also give you an indication because that's telling you how much heat is dissipating. Okay, so you can use your senses in order to tell you some of that. I don't have to know whether the superheat is 30 or 45 to know that the superheat is high. So that's what I'm doing with my hand there. Now, that doesn't tell me the superheat, and that's not enough, but when I'm in the process of diagnosis, I can tell you right there, I can tell you within 15 seconds of hooking my equipment up what's going on with the system. And I tell guys this all the time, because those are the two that get misdiagnosed the most often, are the difference between a system that has low airflow and low on refrigerant. That's the most misdiagnosed refrigerant condition that exists. But I can tell you whether it's one or the other instantaneously, as long as the system's not frozen. If I walk up to a system that's not frozen, I hook up my suction gauge and it reads low, and I see that the suction line is sweating, and I grab it and it's cold, it's not low on refrigerant. If I know it's not iced over. Okay, so I got to check that as well. But if I walk up to it, the suction line's warm or just barely cool, I'm not putting off much heat at the top. Like Larry said, my suction pressure's low, then I know it's low on charge at that point.
As long as your head pressure.
As long as my head pressure, exactly, because that could be a restriction at that point, correct. But by taking, but that's only because I understand the 5 pillars. If I didn't understand the 5 pillars, if I didn't understand what was supposed to be happening here, I could easily get confused about it. Because what is a cold suction line or a warm suction line telling me? It's really just an inaccurate measurement of superheat. Okay, by actually using a thermometer, I can tell you exactly what the number is, right? So, speaking specifically, you know, it's a little hard in a class to go over all of the different things that can happen inside the system, but that's what I've essentially given you there in that list is I've given it to you both directions. I've given it to you saying, here's some common problems and here's the symptoms that you'll see. Here's the symptoms and here's the common problems they could be. If you compare them, use process of elimination to compare the different symptoms and issues. But the best gift that I can give you is getting to the place where you start to interpret and using logic and process of elimination to use the 5 different readings that you can take in order to tell you things about the system. Remember the basics here. Get back to the basics about what causes the different changes in condition of the refrigerant, what affects the pressures inside the system. So break outside of your box of thinking air handler and condenser. You know, that's how we tend to think in the trade. It's not air handler and condenser. It's compressor, condenser, metering device, evaporator. And it can be in any different kind of configuration in order to accomplish the goals that we're trying to accomplish. You with me? All right, well, that's it for today. And we'll